Let's look at problem 2 from this new worksheet. In this problem, I'm introducing a new type of coordinate system. This one will require some visualization and 3D geometric orientation in your brains. So this might be a little challenging. You might need to pause the video, rewatch a few spots. We're getting to some more challenging problems now. So in problem 2, the scenario is that we have a skier skiing down a slope, and we'll assume that this snow and the skis are very slippery, so there's no friction yet. So a sketch might look like this. There's a mountain, and there's a skier. Some skis, and a hat. Here's your skier skiing down the mountain. Now let's draw a free body diagram for this, but I'm gonna warn you, this is kind of weird. Usually, when we draw a free body diagram, we like to choose one of the coordinate axes to coincide with the direction of motion. So since the skier is sliding down the hill, let's make one of our axes, call it the x-axis, line up with the hill. That means the y-axis, which is always perpendicular to x, will be perpendicular to that hill. So in our free body diagram, our coordinate system is now tilted. It's no longer horizontal and vertical. The skier is our object of interest. I placed him at the center of the coordinate system, and now we write down the forces involved. There's always gravity. Gravity acts straight down. Keep in mind, down is no longer along the y-axis because y is tilted away from vertical now. Gravity is still down. That's not the y direction. So there's the gravity force of the Earth acting on the skier. And there's still normal force. Remember, the word normal means perpendicular, so whenever you're in contact with a surface, the normal force is perpendicular to the surface. This mountain or this slope is the surface, so normal or perpendicular to that surface is along the y direction. That is perpendicular. So there's the normal force of the ground on the skier. And for this problem, those are the only two forces involved. Now, I claim that this angle of the hill is the same as the angle right here between the gravity force vector and the negative y-axis. Now, students always ask me, how do you know that that theta and that theta are the same? Why isn't this angle theta or some other angle? So let me draw you a sketch of why this angle is theta. Here's horizontal. Here's vertical. Here's our x direction. There's theta, the slope of the hill. That must mean that this angle is also theta. Now if you draw the y direction, which is perpendicular to x, then this angle has to be theta. That angle has to be theta. But here's our y direction, and this vertical direction is the direction that gravity points in. So if you compare this picture to our free body diagram, gravity is going in the vertical direction. There's our y-axis, so there's that angle theta. Same as the angle theta in this picture. You might need to rewind this part and convince yourself that this is true. Okay, so let's get the components of that gravity vector so that then we can do our Newton's second law analysis. So gravity points down, our y direction is at this angle, and here's a right triangle. If you go back to our original free body diagram, there's a right triangle. So there's W, and there's theta. Here's WX. Notice that is the opposite side of this right triangle to the angle, so it gets sine. And the y component is adjacent to that angle, so it gets cosine. All right, I'll continue the problem now. Erase this stuff. Let's look at our Newton's second law equations. Here's Newton's second law in the y direction. In y, the acceleration is going to be 0 because the y direction was perpendicular to the slope. The skier is not moving perpendicular to the mountain. The skier is moving along the mountain. The skier is not jumping up or sinking into the snow. So that's 0. And in that y direction we had positive normal force, and we had the y component of gravity in the negative y direction. So N equals Wy, and we just did some geometry to figure out that Wy is W cosine theta, and W, as long as you're on the surface of the Earth, is always mg. Okay, so we know a fact about the normal force. That's going to come in handy later when we do friction problems on slopes. In the x direction, sum of the forces equals ma, and there's only one force. It was the x component of gravity that lines up with the slope. So we've got Wx equals max, or W sine theta equals max, and W is mg. Notice these m's cancel out, so we didn't even need to know the mass of the skier, it's irrelevant. And the acceleration of the skier down the mountain equals this expression, g sine theta. Let's think about that expression for a little bit. What if theta equals 0 degrees. Well, that would just mean that your skier is on flat ground, and they're not going to accelerate. That makes sense because sine of 0 is 0. So 0 acceleration. What if theta equals 90 degrees? Well, in that case, your skier is just falling down a cliff. And the acceleration would be .8 meters per second squared. Notice something weird that happens here. This is positive. Usually when we were talking about falling, we said acceleration was negative 9.8. But in this case, it's positive. That's because if you look at our hill, if you look at our slope, there's our angle, there's our x direction. You can see that as you increase that angle, the x direction starts pointing downward. So that by the time you bring that angle up to 90 degrees, positive x is down. So that's what's happening here. Ax is positive 9.8 because the way we set up the coordinate system, increasing theta means that by the time you hit 90, positive x is down. All right, and to answer the actual numerical question posed in this problem, what's the acceleration when theta is 20 degrees? Well, it better be some number between 0 and 9.8. And in fact, it is. It is 3.35.